And that has to do with resolution, but I'll go over that in a second. So that's 5 volts here, we have a sample.
GMS.
Yep.
Yeah. You have another sample here, and those are your 2 samples if you're a sample at the exact frequency of 10 hertz of your signal. So when you go to reconstruct this with interpolation, what your computer does, it says, all right, I'm gonna connect the 0, and I'm gonna connect the 2 samples. So if you look at this, this is definitely not our original signal. What this is called is an alias, which is a complete destruction of the signal. And the reason this happened is because we sampled at the exact same frequency of our signal. So the way we get around this is by oversampling. And there's something called the Nyquist frequency, which is you sample at twice the frequency, but you're still going to have a little bit of aliasing. So if we sample twice the frequency, that means we sample here and here again. And if you put points there, what that will end up looking like, that's about, I'll say 2.5 volts. So that's mid-range here. Put a point here, and then when you go to reconstruct that graph, will end up looking like it's a little like triangular. It kind of depends on what method you use for interpolation, but it ends up looking something like this. So it's a little better, but it's still not the same waveform we have. So what we do in our system for sampling is we do a lot of oversampling. Just because of noise and things I won't get into now for this lecture, we sample at a rate of 10 times the signal frequency. And that actually gives us a very good consistent signal. So for example, if I were to sample at 10 times, I'll get 10 discrete points. So that'll be one there. It's probably not going to line up, but whatever. There's a lot of points, and you start getting your curve. So basically, to simplify this, you sample 10 times your frequency, you get a whole lot of points, and it ends up looking a lot like your sinusoid. So when you go to reconstruct it with your interpolation method, you get a very matching waveform back out in your digital landscape. The reason why this is important is because in microcontrollers and the digital world, you can't speak in continuous talk. This is like 0 to 5 volts. In digital world, it's 0 or 5 volts. There's no in between. So the way the computer sees this is literally just those dots I made earlier, like this. And it has some like frequency or time component that tells it like when that sample occurred. So that's all fine and dandy. You have a sampling rate now, but now you need to tell the computer at what resolution you're sampling at. So here we have a range from 0 to 5 volts. And just for an example, let's say that our system is 12 bits because our Motec system is 12 bits. We'll use that for this example. What that means, since the computer speaks in either 0 or 1, 0 or 5 volts, that means your range of speaking is going to be to the end. And the 12 bits is where this end goes into. So that gives us a resolution of that many bits. So we have this many bits that we can represent this 5 volt range in. And what we do is we say, for every bit, how much voltage can we represent? So the way you do that, super easy algebra. You take 5 volts, and you divide it by 1,023 bits. And that will tell you how many volts per bit can be represented by the system. In our case, our signal varies like largely. You can see it goes from, we'll call this 2.5 volts to 5 volts. So the range of the signal is 2.5 volts. So we don't really need a lot of resolution. So in this case, 5 volts over 1,023 is like 1.22 millivolts. That's perfect resolution. That is more than enough we need to see the 2.5 volt range here. So we know our sampling rate is good because we're getting a consistent signal reconstructed. And now our resolution is good because it's going to actually see the changes in the signal. If we had a resolution that was like just 2 bits, so just 2 to the 1, it would be awful. That's literally either a dot at the 2.5 line or a dot at the 5 volt line. There's no in between. So our resolution would be awful. It would look like a square wave if we were to, look at that on the output of our microcontroller. So that's the analog to digital conversion. And now we can start getting into what we do with that digital data. So once we convert it to digital, the microcontroller or our system, whatever it is, can now talk to itself and other digital computers about what that data means and can modify it to do like various control schemes. But this year, what we care about is delivering all of that information to other computers. There's a lot of ways of doing it. But they mainly fall under two different branches. There's synchronous and asynchronous. Now, CAN is asynchronous technically. What this means is that the rate that the master microcontroller samples is the same as the rate that the receiving device is sampling. So they're synced up together. What asynchronous means is the opposite of that, where the master device is on a completely different like sampling or send out rate than the receiving device. The reason CAN is this way is because it has no like clock cycles or anything to match up the two. It's just raw data coming out of the bus. So a quick example here, I'm not going to go too deep into it, is something synchronous. It's called SPI. That stands for Serial Peripheral Interface. And on that, you have 4 lines. You have an enable. That just tells the like receiving end when data is going to come in. And that's how you actually start your synchronization. So we'll call this right here the enable sequence. And you also have a clock cycle, and that's going to be what's doing the synchronization. So I'll just do something random here. Just a clock up and down, just no pulses to tell when the system is active and when it's not. Because all systems run on a clock. Some are faster than the others are slower. But with this, you can synchronize 2 different systems that have different clocks, depending on what the architecture is. But that's fancy stuff we don't have to worry about for now. The other 2 lines, this is purely for synchronization. The other 2 lines are about data. So it's called master out, slave in, or known as MOSI. And the other one is the inverse. It's master in, slave out. So what happens is the master will send an enable signal, and this tells the receiving device, the slave device, that data is incoming. And you'll hold this low or whatever value to, in this case it's low, you'll hold it low the entire time data is coming. And then the master will start sending the data at every like rising edge of the clock pulse. So this right here is the rising edge of the clock. This right here is the falling edge. There's a lot of like architectures out there that allows you to swap these variables around, but just for the sake of simplicity, we'll have it be set up on the falling edge and sampled on the, or set up on the rising edge and sampled on the falling edge. So on the rising edge, the master is going to set up the data. We'll call it a 5 volts. So if we have a 12-bit system, 5 volts is literally going to be all ones. So this entire line would be high. This represents, the 12 bits that are all entirely high. So that's all the way to 12. So this is going to be held high. And every time a pulse happens, the receiving device is going to sample the bit right here. So it's going to go down and sample, and it sees a 1, it collects info on that. It will sample again here, it sees a 1 here, and it keeps doing that for the 12 pulses. And that's how SPI works. So the reason it's called synchronous is because of these 2 things right here. The receiving device will not look at the data until it sees an enable, and the clock cycles are synchronized with the master, because the master is the one that provides this clock cycle. Now, the interesting thing is CAN does not need this. CAN just does whatever it wants, and it's basically like a giant like cafeteria where everyone is shouting whatever the heck they want at any time. So the way CAN works is there's no 4 lines, there's only 2 lines. There's a CAN high and a CAN low. And really, you can read off of this with only 1 line, but again, I'm mentioning fancy stuff you don't need to worry about. You can have like a bus of these 2 wires going literally anywhere. So for now, I'm not going to draw like what the code looks like. I'm just going to draw like what a CAN system would look like. So we'll take this line, simplify it a little bit, and we can draw our system on the car. So in our car, we have the 3 main Motec devices, the ADL for data logging, the PDM for power control, and the ECU for engine control. So this will be our ADL. That is going to collect all the data and send it out to our other 2 units to use for like logic and control. So I'll draw those just down the line. The ECU here, it's our engine control unit. We use that for various engine-related things like traction control, launch control, and engine tuning, all that fun stuff. We have PDM here. That's your little power device. So your CAN bus, what it does is it takes two wires, attaches all three of these devices together, and over those two lines, there we go. Over those two lines, all three of these devices can share whatever information that they need to. Now, what's special about this is this year, we can actually hook up our own devices to this bus here. So on this bus is literally everything that the ADO records, like any data that these two devices need, the ADO can put it out, and both of these can sample them simultaneously. There's like no clock cycle or enable. If you remember earlier when I was talking about SPI, when you enable the receiving device, only that one device can talk on the SPI bus. Sometimes. For now, we'll just say it's only one device at a time. Nothing in like, there's not going to be a device in parallel. Like, it would be very complicated with SPI to have these two on the same like enable bus. Because sometimes the PDM will need data that the ECU won't, and sometimes the ECU will need data that the PDM won't. So if you do that over SPI, you can't have like the same enable line for both, because otherwise it'll be like storing in information that one doesn't need. So the beauty of CAN is you can send a message with an identifier. So I'll try to draw the message out. I don't really have it memorized that well, but it starts off. It'll just be a box for the sake of like simplicity of when it ends and when it starts. You have this like first box that is called the identifier. Maybe it's the arbitration, but this is basically the ID. It tells the entire bus who the message is meant for. So let's say the ADO wants to send data purely to the ECU. So there's going to be an output of, let's say, we'll just say GPS is one of the outputs. It wants to send GPS data to the ECU because we're using it for grounding speed for like traction control. That'll be our example. So the way it's going to do this is it's going to set an ID that's specific to the ECU. So for example, this is in hex, which is a different way of representing numbers. So our ECU address is 0x3AB. What this ID is going to be is it's going to match that. So what that's basically saying is that this message is purely intended for the ECU. So if we go over to the PDM, we'll assign another random address. We'll say it's like 0xFFF. There's some random numbers. They don't really matter, just for the sake of showing what's going on here. When this ID goes out, the ECU and the PDM are going to look at the message as it goes down the bus. And the PDM will look at the ID, see that it's 3AB. It will compare it to its personal identifier. And once it does that, it says, I don't care. I don't want to read the rest of this message. So it stops right there. So after that, it doesn't really care about this message here. On the ECU side, it looks at this ID and it says this message is important. So it will start looking at the rest of the contents of the message. For now, we don't have to care about the like fancy redundancy checks and ways of making sure the messages don't die. We'll just say that it's an ID and a data bus. So all of our data will be here. When it sees the ID, it will start reading the rest of the data. And it does it in a similar fashion as the SPI, where it reads like one bit at a time. So if this was like something like 11011, I can change our little graph here to kind of match that. Goes down, up. That's what it would look like. It looks for those pulses, and then it records the data, and it records whatever this value is. I did say that CAN isn't synchronous or is asynchronous. It is true that it's not. The way it does synchronize is this ID bit here. As soon as it sees the ID bit, it will synchronize with this like high value here, and that's how it's able to read the data here. And actually not like mess up the bits or anything like that. There's some other parts of the message. I don't know if we want to get into those about how it reads it right, but do we have any questions so far? Let's kind of sped through this. Nothing? Okay. So we'll get into some of the fancier modes of CAN communication. What makes it so amazing? So one of the concerns you might be thinking is, sure, this is just like one instance on the bus where data is coming out and going in somewhere. But because I said it's asynchronous, anything can happen at any time. Like I said earlier, it's a bunch of people shouting at a table and you're like listening for some trigger word or whatever. So GPS data is not the only thing on the CAN bus at a given time. There's like multiple things being skewed on the CAN bus. Like we'll have like wheel speed data, I'll just call it speed, SPD. We'll have like oil pressure, just like anything you can think of is probably on the bus. And they're not always going to be sent at the exact same time, which is the beauty of it. We're fine if they're not sent at the exact same time, because our speed is 1 megabyte per second. And what a byte is so 1 byte. I don't know if you learned this in your programming classes. 8 bits. Remember, our system is, I erased it, but our system is 12 bits. So 1 megabyte is, oh, that's the weird one. I think it's like this many bytes. If I remember right. No, that's right, Lucas?
Yeah.
Okay. So that's what it is. That's how many bytes it is. And that's how many bytes it is per second. So it's insanely fast. On our car,
Kilobytes.
oh, right. Yeah. There we go. All right, now we're good. So it's insanely fast. We're never going to get at that rate on our car, hopefully. Right now, we're only running about 20% of this speed here. So there's a lot of data that could be on the bus. Getting back to what I was getting at before, so we have all these sensor data like going on the bus. Because it's asynchronous, we might have like 1 millisecond GPS data comes out, that's okay. And then like at the second millisecond of the system being active, there'll be like oil pressure coming out. Now what happens when 2 pieces of data come out at the same time? And that's one of the issues with asynchronous communication, is because so many things are happening at once, they can actually collide. So the way CAN deals with this is something called arbitration. And before I said ID was the first kind of bit on the CAN message, but it's actually the arbitration. So I'll call it ARB for now. And then after it is the ID. Now that we're adding things now that we learn like how the basics of CAN works. So arbitration is the first thing on the message. The reason for this is when 2 messages are sent over the CAN bus. So we'll call this like message 1. Get this out of the way to make it a little less confusing. So this will be message 1. This will be message 2. So they're sent at the exact same time. What happens on the bus is we look at the arbitration, and on CAN bus, the low values of CAN actually cancel each other out. So remember how we had your CAN high and your CAN low. When you have a value with a low bit, so this isn't just like one block. There's actually a lot of bits in here. It's like there's some random data in there. It's actually just a 1 or a 0 if I remember right. But this isn't just like a block. There's a whole section of data in there that the CAN protocol will look at. So the way arbitration works is when there's 2 messages and they collide, there's going to be a set priority. So for instance, if we have like throttle position versus airspeed, throttle position is way more important to us. So we're going to set a higher priority arbitration. So when the 2 messages collide, the throttle position message actually takes priority. So the way that would work is when 2 messages happen at once, they're both on the same bus. So they're both on the CAN high, the CAN low are being sent here at the exact same time. But the way it works is they start colliding and it's destructive to the, what did I say, airspeed? Yeah, airspeed. So the airspeed message is going to die. I'll just call this airspeed. Starting right quickly. And this will be our throttle position. So our throttle position is going to take over because its arbitration is a bit value that is higher priority than the airspeed message. Since we're not all like EEs and CEs here, allegedly, I'm not going to go over like what the bit values actually are. You can go look into that later if you want to, or just ask me about it. I'm also using that as an excuse because I don't remember. But anyways, it's a lower value. It takes over on the bus, and the rest of the message is just thrown out. You would think that airspeed is now screwed and you lost that data permanently. That's not the case. At the very end of the message is something called the acknowledge bit. When a master sends out a CAN message, it's going to have an acknowledge bit at the end that is either a 0 or a 1. And it's a 0 when it's not acknowledged, and it's a 1 when it is. What happens when you send a message out is it goes out, it goes to the ECU, and then whatever receives it will change this acknowledge bit to a 1, and the ADO will see that and say, okay, my message has been heard. I don't need to shout again. What's interesting about this is, let's say that the message was intended for the ECU, but the PDM takes it just because it uses something like non-critical for it. What could happen is that the PDM acknowledges that they received the message, but some awful thing happened to the ECU, like this line was cut or something, and the ECU never received the CAN signal. The PDM will still change this acknowledge bit to a 1, so it says the message is acknowledged, and the ADO will think that the message is all good and doesn't need to send it again. That's kind of one of the issues we have with CAN. In our case, there's very few instances where we have something like non-critical that one unit needs that the other one also needs. So we're okay in that regards. That's one of the kind of pitfalls with the ECU. But obviously, if a CAN line is broken in the ECU, you're going to be warned about it sooner or later. So it doesn't really matter that much. Getting back to arbitration and acknowledgement, if the arbitration allows the message to be killed, like in the airspeed case, you're going to have a 0 on the acknowledge when it returns back to the ADO. So now the ADO knows that TPS went out, but airspeed did not. So what it's going to do is, once it sees the acknowledgement that TPS has been received, it's going to send out airspeed again. And depending on how you set up your system, it could keep trying to send out airspeed like forever. But in our system, we have it set up intelligently, so it only tries after so many times, and then it will give up. That's just kind of one of their redundancy checks for when 2 messages collide in an asynchronous system. How much time we have left? Oh, that's probably kind of short. So any questions? Kind of a brief overview of CAN, and I definitely jumped over a lot of things. Anything? All right. That's all I got. Dang. That good, huh?
Jumped over so much, I don't know.
Yeah, it was very,
Or
very,
you
very
did it
fast.
over.
There's a lot of stuff in like how microprocessors work fundamentally that you kind of have to understand about like messaging.
Right.
And that would be like an hour-long
Yeah.
discussion.
Like a full, like a legitimate.
An hour is generous.
The most important part of this was the whole analog to digital thing. So as long as you got that, then that's good.
Yeah.
Well, I guess I kind of skipped over how analog turns into bits, right? Do you understand that?
No, the sampling rate, right? And when you sample it. Like,
Yeah, the
that's
resolution.
Yeah, the resolution. Yeah.
I was going to draw a graph, but of course I forgot about it. There's something called, I was called the resolution graph. You have like your bits down here. You have your voltage here. For our system, about 5 volts. So that's 0 here. You have your 12 volts, your 12-bit system here, and we'll just have like a linear line. So remember how I said that 1 bit represents the 1.22 millivolts. So that means like every discrete bit, the 1 or the 0, is going to represent like every 1.22 millivolts. So the way that would work is you have your like analog signal here, and it kind of looks like a step function. Like every every like block like that is going to be 1.22 millivolt, and every block here will be 1 bit. So as you go up and up, it kind of looks like a very interesting like step function. Unfortunately, I inverted the way I'm supposed to draw it, but it looks something like this. As you get higher and higher, it like goes up and up. You can already kind of see the issue with having a low resolution system. Like this analog change, so let's say this is like a 0.15 volt change. If we didn't have a high resolution like we do, we would completely miss out on this entire change of analog voltage. So that's one of the reasons it's important to have a high resolution system. So if we were using like strain gauges, for example, that's operating at something called microvolts. So that's even less. And that's what our system would look like if we had a 12-volt system. Like you can see this much strain, this much voltage, and our system would not even be able to represent it at all. Like it would take a lot of sensor like strain and stress, whatever it is, a lot of sensor data coming out of our device to actually change to the next step up in the digital realm. So depending on what you're doing, you might need a higher or lower resolution than 12 bits. For the example I used earlier with the 5 to 2.5 volt system, 12 volts is definitely overkill because the system is changing by a whole like 2.5 volts. But for something where you're working in like microvolts, it could be very expensive to upgrade your system to 24 volts. So you do something called amplification, where you step up the gain on your signal. So it starts off super small. You'll put it through some fancy circuitry here, and then it becomes like that. It becomes very big, and then this can see it. So, and for our strain gauging we're doing this year, we're amplifying it, and that's how our 12-volt system can see it. We do that for cost reasons mainly, and also because 24 bits is kind of annoying to work with. Because your data will be 24 bits, but your system is still 12 bits. So it's kind of hard to like smash that all in.
When you say amplifying that, is that like raising the voltage of the signal? Or?
It's kind of like, you think of it as mapping. But yeah, you're essentially raising the voltage. You have like, you can say an input from 0 to like half a volt will map to 0 to 5 volts. And that would be an amplification of 10.
Yeah.
So like that. Simple way of looking at black box amplification. Anything else? No? Okay. Kept it all short.
Nothing on the Zoom people side?